literally this entire semester has just been like.
We're going to continue. Can I have your attention, everybody? We're going to continue with our discussion of magnetism. Last time, the discussion was magnetic forces, okay? And who experiences them? It was moving charges experience magnetic forces. A moving charge in a magnetic field will experience a magnetic force. So, moving. So consider so a charge Q with velocity V moving in a magnetic field E will experience a magnetic force FB. The magnetic force that we experience, this is FB, and it was the charge, the velocity, and then the cross product with the magnetic field in which the charge is moving, right? This is the force law. If you have a single charge, you get this. If you have a current, then you would write the velocity as ds dt. This would be dq. So you would have current cross product with the ds with the magnetic field, and then you integrate to find the total force on a current, on a segment of current, right? So we did this last time. Now, the next question becomes, how do you produce magnetic fields? Or what produces magnetic fields, and how do we calculate them? So, the short answer is, you see, moving charges in a magnetic field experience a magnetic force. If the charge is not moving in the magnetic field, then the magnetic force will just be zero. Now, who produces magnetic forces? Magnetic fields, sorry. The answer is moving charges. So moving charges, they produce magnetic fields. And then the next question becomes, okay, I have a charge that's moving, how much magnetic field is it producing? So that's the next. So let me write it here. So magnetic charges for moving, I said magnetic charges, I meant moving charges. Which means, in another way to say current, produces a magnetic field. Okay? So moving charges, they produce magnetic fields. Now the question is, how much is the magnetic field and how do we calculate it? What's the law? That law is called the Biot-Savart law. It's similar to Coulomb's law for electricity, but this one is for magnetism. And then we will learn another law called Ampere's law. When you have symmetry, then you can take advantage of symmetry and find an easier way to find the magnetic field. Okay? So here is how the law says. So suppose I have a current. So here is current, I. The current I moving in a current wire. Okay? It doesn't have to be straight, so that's why I drew it like that. But the current is like this. So the charges are moving along the wire, right? The question is, what's the magnetic field due to this wire at a point P? So let's say this is a point P. Point P is where I would like to find the magnetic field at due to this wire. So what we do is we slice the wire into many little pieces. So here is a little piece of the wire, and this is a segment ds, and ds is tangential to the wire, or along the wire. That's ds. And let me draw a vector that points from ds to P, and I'm going to name that vector R. Vector R. And this is ds. So what's the magnetic field produced by just this segment of the current, ds? Okay, what's the magnetic field produced by just that segment of the current? The answer is the Biot-Savart law. You can't derive it. It's just a law or an experimental fact. And it says this. The magnetic field produced by just that segment, we're going to call it dB, is equal to a constant called mu naught. We'll see what the constant is in a second. It's similar to epsilon naught, mu naught. The current in the wire, I, divided by 4 pi, and then ds, the cross product with r hat over r squared. R hat is a unit vector along r, so r hat is also in this direction. It's r divided by its own magnitude, right? That's what r hat. So we can rewrite this in terms of the vector r. It would be u naught I over 4 pi ds from r over r cubed. And we encountered this r squared and r cubed before, right? With Coulomb's law, where we just replace the vector r hat with the vector r divided by its own magnitude, and we have r cubed to the power. Now, how much is u naught? Well, first of all, they have a name for it. We don't really need it. It's called the permeability of free space, but it's a constant. So mu naught is equal to this. Mu naught. It's exactly 4 pi times 10 to the minus 7 Tesla meters per m. Okay. That's the magnitude of mu naught. That's how much mu naught is. We will see that epsilon naught and mu naught together, they're actually related in some way to the speed of light. Mu naught and epsilon naught, they're related to the speed. We'll come back to that, but for now, this is mu naught. And this is the law. Okay? And a big segment of today and next time will be to learn how to use this. We're going to apply it to certain configurations on how to calculate the magnetic field. These are the same, right? I want you to notice the 1 over r squared, right? The 1 over r squared. See the magnetic field drops as 1 over r squared as you go away from the little current. Similar to, remember, or look at the similarity between the electric field, for example. It was k q over what? R squared, right? And then you have r hat, right? So the magnitude of the electric field is just k q over r squared. How about the gravitational field, G? It was capital G M over r squared, right? The magnitude. Right. So it also goes as 1 over r squared, which is interesting, right? Magnetic. Electric force, magnetic force, and gravitational fields. Okay. So that's that. So how do we apply this law to calculate magnetic fields due to currents? So let's start with the simplest case, which is a straight wire segment. No curves, no wrinkles or anything. So it would just do this. So example 1. Suppose I have a wire, and this is the x-axis. I would like to know what's the current due to this wire. What's the magnetic field due to this wire at the point here? And let's say that point is a distance a from here. This is distance a, and the current running is I. Okay. Suppose our current starts at the segment I want to consider. Not for the whole infinite wire, but just a segment of the wire. Let's say the segment, the wire I'm interested in starts here, minus x left, all the way to x right. XR is right. I'm just trying to make it maybe not, it doesn't have to be symmetric. I don't have to say from minus L to L. I'll just say left to right. Okay. So what's the magnetic field due to this? So notice the current is this way, is along the x-axis. So ds, that ds, that I'm going to plug into this equation, will run parallel to the y. So I'm going to write here, notice that ds is simply equal to dx, and it's in the I hat direction. So here is ds. Let's draw. Here's a little segment, ds. That's our ds. Next, draw a vector from ds to the point where you want to find the magnetic field. So that vector will point this way. That's the vector r. And in order to write down what the vector r is, so this distance this way, this is x, right? Let's call it x. So the vector r will be, it will take you a distance x to the left and a distance a upward. So it is minus x I hat plus a j hat. Do we agree with that? That's the vector r. Takes you x left, a up. So let me write down the vector r. That's the vector r. Which means that the magnitude of the vector r would be x squared plus a squared square root. And that means that r cubed would be x squared plus a squared to the 3 times. We're getting set to use this equation. So this equation consists of this cross product. I need to figure what ds is. I need to figure out what r is. And then after that, I know what r cubed is. So I need to do the cross product next. So the cross product, ds crossed with the vector r would be dx I hat. Cross product, I would put cross product with yellow, so this is not x, this is times, so cross product. And then the vector r, which is minus x I hat plus a minus j hat. Okay, let's look at the cross product. The cross product, dx I hat, and then let's do the first term. What is I hat crossed with I hat? 0. Good. A unit vector, if they're parallel, their cross product is 0. Good. And then I hat cross j hat is what? K hat. Good. I hat cross j hat is k hat. Good. So therefore I get a, and then this cross product becomes k hat. This one drops, right? It's a 0. So you get this a dx, or just right here, becomes a dx and then k. Okay, that's what it is. Now we can write what dv is. dv is u naught I over 4 pi, and then ds cross product with vector r over r cubed. Just like we did, by the way, with electricity, sometimes we use, this form is convenient to use, sometimes the bottom one, the one with the r cubed, is more convenient to use. Most of the time it's this one that's more convenient, because I don't have to find the unit vector, I can just use the vector r. That's why I use this one. So I get u naught I over 4 pi, and then I have a dx k hat over that stuff, x squared plus a squared to the 3 times power. So the magnetic field, we will to find the magnetic field, we will integrate. So you get B will be u naught A over 4 pi, all of these are constants. I will put my, this one, the k hat, let's just keep it in front so it doesn't bother us. And then here we get dx over x squared plus a squared to the 3/2 power. And now we need to do our integral sign. And the integral clearly runs from where to where?
Minus x.
Good. For the limits, minus xl to positive xl. This is not our first time encountering this integral. We have encountered it before in electricity, so we can just look up the answer. And I'm going to just look it up. I'm going to do the integral. So that integral becomes, let me just write down the front part first. So k hat u naught I a over 4 pi. It's x over a squared root of x squared plus a squared minus xl positive xl. Yes. Now, a, this one cancels, and so we get k hat u naught I over 4 pi a xr over xr squared plus a squared. And technically you'll have minus, but then xl will have a minus sign when you place it on top. Minus minus becomes a plus. So that's why it turns to a plus. xl over xl squared plus a squared. Actually, let's write the k hat back to the front. So that's the magnetic field due to a finite wire segment, a straight finite segment. That's the magnetic field. Now, this one is just an intermediate step, or it's just an exercise to find the magnetic field, to get some practice with this. But I'm actually interested in very long wires. So if the wire is very long, it means it extends from minus what? XL is infinity, but minus, right? And then XR is infinity, but plus. So XR will, what's the limit as XR goes to infinity? Yeah, this thing will just be 1. That limit is 1. And how about this limit when XL goes to infinity? Also 1. And so 1 plus 1 is 2. You have a 4 here at the bottom. So for an infinite wire, meaning XR and XL both go to infinity, the magnetic field is u naught R over 2 pi times A. That's the magnitude. The direction is, if the wire runs from along the x-axis, it will be the k hat direction, right? I'm going to redraw this. I'm going to redraw this one from here, infinite wire. I mean infinite straight wire, right? So here is the wire. That's the current. Wire. And let's say we're a distance r away. A distance r from. What would the magnetic field the distance r from the wire? We called this A earlier, right? I'm going to call it R now. What's the magnetic field? U naught times I over 2 pi what? Now the A became R, right? I'm calling it R now. So as long as I'm the same distance away, the magnetic field will have the same magnitude, right? And so let's think about the direction of the magnetic field. We said here's the wire, it's going to the right. The magnetic field is in the k hat direction. Where is the k hat direction? So this is, yeah, let's say this is x and this is y. You said toward where? Towards you. Yes, yeah, that way, out of the board. So yeah, so the magnetic field will be like that, towards you, above the wire. How about here, below the wire? Yeah, so just, I guess, go behind the board and look at it. So it would be in. It would be into the board. So here, the magnetic field comes out, and then it goes in. So here's one way, there is another right-hand rule. There is the right-hand rule that you use to calculate cross products. But this one is the right hand, how to use your right hand in order to figure out the direction of the magnetic field given the direction of the current. So it says this: take your thumb and align it with the current. So here is the current. Your fingers will loop around the current, will go around it like this. So if this is the current, the magnetic field here will be coming out. That's where my fingers are pointing. And here, it will be going in. So the magnetic field will be doing this. It loops around the current. There? So here is another one. So let's say, let me ask you the following. I'm just going to, let's say I reverse the current. Let's say the current now runs this way. Here is I. The current is running this way. What would you say? Your thumb with it, right? So the magnetic field will now come out and go in. Yeah. So the magnetic field will come out here and you go in. How much is it? That's the magnitude. How do you find the direction? Use your right hand. Let's do another one. How about if the current now is going up? If the current is up. Yes. That thumb. And so the magnetic field would be out here and would be going in, right? And I guess one more. Here is the one more. Now suppose the current, so what I'm going to draw refers to the current, not the magnetic field. Suppose now the current is coming out of the board. So here's the current. Coming out of the board. So this is the current. So imagine it's a wire that's coming out of the board like this. That's the wire. In what direction is the magnetic field? Yeah, your thumb, and this is the magnetic field, so it would be counterclockwise. So that's a side view of it. So yeah, so the magnetic field so for straight wires. Now just to get a feeling of how big is a magnetic field from an infinite wire, let's say you have a wire, it carries 1 ampere of current, which is large. So here's the wire. Let's say, suppose I is 1 ampere and R is 1 centimeter. So you're really close to it, just a centimeter away from the wire. How much would the current be? I'm sorry, how much is the magnetic field? Well, just plug in the numbers. V for this case. It'd be mu naught I. How much is mu naught? That. Yeah. So 4 pi times 10 to the minus 7 times the current, which is 1, right? And then over 2 pi times R. And R is 1 centimeter. That's 10 to the minus minus 2 meters, right? And this turns out to be what? 2 to the minus 5 Tesla, right? So this is 0.2 Gauss, right? Remember Gauss is 10 to the minus 4 Tesla? That's just another unit. I'm just comparing it. The magnetic field of the Earth, we said, is about 0.4 or 5, 0.4 or 0.5 Tesla. Gauss, sorry. So this one is even less than the magnetic field of the Earth. So it's weak, even though you have a very strong current and you're really close to it. So this is not the best way to produce strong magnetic fields, but coils will be the way to produce strong magnetic fields. Yes. So and we're going to do that next. Let's do this question. Suppose we have a current that's going this way. Here's the current, I. So this is an example. Okay, that's an example. Now the current that's going from left to right, the current is going from left to right, and let's say the current is 10 amps. So I is 10 amperes. That's the current in this wire, 10 amperes. And we have an electron that's 1 centimeter above it. So here is the distance. R is 1 centimeter. And we have an electron here. Electrons are negatively charged, right? Electrons are negatively charged. Suppose the electron has a velocity v in this direction. The velocity of the electron is 1 times 10 to the 7 meters per second. And actually, let me just not even, or yeah, let's say this is 5. Question is, let's first ask, in what direction is the magnetic field? Where the electron is there, so the magnetic field must be coming out, right? Why? Well, the current is this way, your thumb, and so the magnetic field must be coming out. So that means this. The magnetic field must be V, and then it's K hat, right? It's coming out of the board, so the magnetic field is in the K hat direction. Okay, how much is it? Let's figure it out. So B will be mu naught I over 4 pi R over 2 pi R, right? We essentially did this. We got this number, but for 1 amp, right? For 1 amp, we got this number. So I just need to put 10 here. So it'll be 2 times 10 to the minus 4, right? So it would be 2 times 10 to the minus 4 decimal. So that's the magnetic field. Now the question is, what's the magnetic force on this electron? And in what direction is it? So without doing the calculation, we're going to do it mathematically, but we're going to just qualitatively. The electron is moving to the right. The electron is this way. The magnetic field is this way. In what direction is the force? Positive J hat? What do you need to do to find the force? Now, right? You do V cross B, and then you look at the charge. The charge is negative, right? It's an electron. It's minus. Yeah, so you need to, so the magnetic field is this way. So V cross B will be down, but the charge is positive, so the force would be that way. So it's a repulsive force. So the magnetic force would actually be upward, would be in the positive I hat direction. Let the math do the job. Okay. Here it is. The magnetic force is going to be Q B cross B, right? What's Q for an electron? E or minus E? Yeah, it's minus little e. Again, this is an electron. V. V is that 10 to the 7 I hat, right? How about B? Actually, I need the cross product. How about B? It's this, right? 2 times 10 to the minus 4 K hat, right? That's the magnetic field. Okay. We will plug in E in a little bit, but for now. What is I hat cross K hat?
Negative J.
Huh?
Negative J.
It has to be
Negative J.
either J hat or minus J hat, right? If you, it can't be I hat, it can't be K hat, right? So it has to be the other one. It's J hat, it's actually negative J hat.
Negative J.
I hat cross K hat is minus J hat, and minus J hat, there is a minus sign waiting, so it becomes plus J hat, positive J hat. So it becomes this. So I have, it becomes just this, and then, well, this is 1.6 times 10 to the minus 19, and then 2 times 10 to the 3, and then J hat, right? So this becomes 2 times 1.6 is 3.2 times 10 to the minus 16 J hat. It's newtons, right? Of course. Newtons. J hat direction. Huh? Why is it there? It's just I hat cross K hat is equal to minus J. You can use the cross product. I mean, you can use the right-hand rule. Yeah. So in what direction is I hat? That way. So let's say this is this is I hat. Where is K hat? K hat is coming out. So you need to curl your fingers from the I hat to the K hat. It's hard. So I hat is there towards K hat. So. Or, yeah. So that's that. All right. So next time we're going to do a ring of, not a ring of charge, but a ring of current, or a current loop. And it will involve kind of three-dimensional thinking. We want to know what is the magnetic field along the axis of the ring or the loop. It would be a circular loop. So let me pause here.